Kia ora, Year 11 and 12. This is question 2E from last year's calculus paper. It's an excellence question, and it's one that I'm going to go through quite slowly because it goes over a whole lot of important ideas. So it's all about finding the stationary points, or turning points, for this function. So we're given the graph of this function, and we're told that it's got a turning point at x equals 3. The first thing that I'm going to do before I go too much further is think about what that function looks like. Now we know that it's a cubic and it's a positive coefficient cubic, right? So the shape of that function is going to be this. And we're told that there's a turning point at x equals 3. And you can see that we're going to have two turning points. We're going to have a local maximum here and a local minimum here. We don't know much more than that yet. We have to use calculus methods to find the coordinates of both the turning points, and then we have to determine their nature, justifying our answer. There are 3 methods to do this, and in this video I'm going to go through all 3 of them, even though you just have to do one. So the first thing to do is to say, well, what do I know about a turning point? Well, a turning point happens when the gradient is equal to 0. So we have y equals x cubed minus 6x squared plus kx minus 5. So we're going to write down at a turning point, we know that dy by dx will be 0. So we'll start off by differentiating, and we get dy by dx is equal to 3x squared minus 12x plus k. And we know that we've got a turning point at x equals 3. So at x equals 3, dy by dx is equal to 0. So substituting in 3, we get 3 times 3 squared, which is 9, minus 12 threes, plus k is equal to 0. So 27 minus 36 plus k equals 0. Now what? K take away, that should be 0. K take away 9 is equal to 0, giving me k equals 9. So now we've actually done all of the hard thinking in this question, because we've figured out the value of k. And that means that if I go back to the start, we now know that that k in here is 9, and we can just get on with it. So we can write down this: y equals x cubed minus 6x squared plus 9x minus 5, and dy by dx is equal to 3x squared minus 12x plus 9. Right, so we need to figure out when that is equal to 0. So we can divide everything through by 3, and we get x squared minus 4x plus 3 is 0, and we can factorise. We already know that x equals 3 is one turning point, so that's a clue for our factorisation. Or if you wanted to, you could do completing the square or quadratic formula, or even just chuck it into your calculator and show you're working. You know what I think of that. Right, so now we've got 2 values. We've got one when x equals 3 and one when x equals 1. Right, now we have to give the coordinates of the turning points, so we need to figure out the y value for x equals 3. So when x equals 3, y equals 3 cubed, so 27. So I'm just working back with this equation now, substituting in x equals 3, 27 minus 6 nines are 54 plus 27 minus 5. So that works out to be negative 5. We do the same thing for x equals 1. So when x equals 1, y equals 1 cubed is 1, minus 6 times 1, 6, plus 9 ones are 9, minus 5. That gives me, let's see, I'm getting 10, that's a 5 there, 10 minus 11, which is negative 1. So my 2 points are 3, negative 5, and 1, negative 1. But let's go back to the question and see what we have to do with those. Well, we've found the coordinates of both turning points, but now we have to determine the nature of each, and we have to justify our answer. So here come the 3 ways that we can do this. So method 1 is what I call the shape of f of x. Right, so y, or f of x, is equal to x cubed minus 6x squared plus 9x minus 5. this is a cubic with the following shape. So it goes like that, whoosh like that. Therefore, this one here, 1, -1, and the other one is at 3, -5. So we can see that 1, -1 is what we call a local maximum, and 3, -5 is a local minimum. Now, one more time, why am I using that word local? Well, the word local means in the neighbourhood, and that has quite a strict mathematical meaning, but it means what it means in real life, that around this area, in this neighbourhood, this point here is the highest we can get on the function, so it's a local maximum. But there are other points up here you can see that have higher values, right? So it's a local maximum, and the same thing here. Around this neighbourhood, this value is my local minimum, right? But there are other places on that graph that are going to be lower, like all of these ones down here. But that doesn't stop us finding these points very interesting in lots of calculus problems, either ones like this or application problems when you get further into calc. Okay, so that's method 1, and that's fine at level 2, and I think it's quite a nice, quick way to do it. If you've got a cubic, you can just use the shape of the cubic. Now the second way is to use the second derivative. Right, and the second derivative is looking at how the gradient is changing. Right, so we've got dy by dx we already found. dy by dx was 3x squared minus 12x plus 9. So the second derivative is very easy to get. The second derivative is just 6x minus 12. And we just have to work out the sign of the second derivative at each of those points. So at x equals 3, the second derivative is equal to 18 minus 12, and that's 6. And that's positive, so that means we've found a local minimum. And I'll show you why in a second. At x equals 1, we've got our second derivative is equal to 6 ones, so 6 minus 12, which is -6, which is less than 0. So that means we've found a local max. Now you've got to have a good grip on this, otherwise you're pretty likely to go on negative number means a minimum. It doesn't. It means a maximum. Okay, so let's look at what's happening. And again, I'm going to do it with looking at, let's look at the cubic here. So if I look at this side, I've got a gradient where I'm doing that yellow highlighting. My gradient is positive, but my gradient's getting lower as I come up here. Right, so if you think about how the gradient is changing, the rate of change of the gradient is negative coming up here. Right, so let's do that one more time. Oh, now I've taken everything away. Right, so as I move up here, the gradient's positive, but it's getting less positive as I approach that maximum there. Okay, and then look over at this one here. The gradient here is 0. As I move over here, the gradient is positive and it's speeding up. So that's giving me the second derivative here being positive around this point here. Okay, so that's a little bit of intuition behind that second derivative test. We'll do more on that in class. So if you're watching this, just treat that as a bit of revision. Okay, so that's the second method. So we've got two methods now. The first one was the shape, using the shape of the fact that it's a cubic to say that this must be a max and this is a min. The second is the second derivative test. Most students in my classes tend to like that one the best by the time they get around to the November exams, but it's a bit strange to start with. And the third method is good, but it's a little bit clunky and it's a wee bit more work. But it shows you, I think, what's going on in the best way, and that's doing a table of values for the gradient. So here we're going to have the x value, and we're going to put in the x value where we've found the turning point. So we'll start with 1, and then we say, well, what do we know about the gradient in the neighbourhood of that? So we know that at x equals 1, the gradient is 0. So we can draw that picture out like this. So put a third column. If we go a little bit below that, so we'll make it 0 and 2 to make it nice round numbers, we can figure out what the gradient is at those places. So what was my gradient function? So there's a wee bit of substitution. Right. We've got 3x squared minus 12x plus 9. So what we're going to do is we're going to substitute in 0 and see what the gradient is. So I get 0 minus 0 plus 9, which is 9, and that's positive. So I've got a positive gradient below 1. And then I do the same thing. I put 2 into that function, and I get 3 fours are 12 minus 24 plus 9. That gives me, what, negative 3. So I can see that there I'm tracing out a negative slope. And what that's showing me visually is that I've got a maximum at x equals 1. And then I can do the same thing for the other one. So hopefully what you're going to see is that you have got a choice. All of them have got a little bit of work, right? But they're the same every time you hit a question about justifying the nature of the turning points. So if we do that again for the values around 3, we know the gradient is 0 when x is 3. The gradient at 4 is 9, which is positive. And the gradient at 2, we already found, was negative 3 from up there. So you can see that we're tracing out a minimum at x equals 3. Okay, that's a long video for one question, but there's a lot in this. And this is kind of a classic calculus problem, right? Finding the turning points. And often, the way to make it a bit more interesting at level 2, and you'll see this when you go through lots of old papers, is things like this, where we don't know k, but we're given some information. So it really makes you think about what I can do with the information about having a turning point at x equals 3. If you go back through some of the old exam playlists, you'll find quite a lot of other hard questions like this. So just email me if you've got problems with any of them. Thanks for watching.